In this video, we are going to talk about some of the instrumentation of light microscopes. So I want to revisit the image that I showed you in one of the first videos. And this is a simple compound light microscope. And we'll just revisit some of the components that we talked about, but then we're going to dig in a little deeper on each of those. So as we can see here, and in the inside view here, the main components that we've talked about and we'll expand on is the illumination system. So this is the lamp, the condenser, everything that's sort of involved in forming light for the light microscope. We also have the objective lenses, that the part that actually gives us the magnification and image formation. So basically one of those critical pieces. We have the eyepiece, which is going to be important if you're using, if you're not taking digital images, if you're just viewing it with your eye beforehand, usually, because most of the time these days we want to get digital images. We also have the photo micrographic system, and that's what's actually going to give us the capability of recording images, so the computer and camera associated with that. So typically that digital camera system will be on top near the eyepiece. So this is kind of the place where you'd see that. I think you kind of see the inside view of that here. So that's what feeds it to the computer. And then we also have the stage, which allows us to position the specimen in the X and Y direction, but also the Z direction. So we can move on the specimen surface, but also move the specimen in the optical axis into the right position for focusing. All right, so when we talk about these different components, one thing to keep in mind is that there are two main types of light microscopes, and they really refer to what type of light is used to collect images. There's transmitted, where we have very thin transparent materials or semi-transparent materials, such as polymers, biological specimens, or just thin sections. And so we look at the light that goes through that material, and that's what's forming the image. So that's one type that we have. The other is reflected light. And so this is typically something we would use in the metals community for looking at surface and microstructure features of various metals, but also ceramics and other materials. It doesn't have to be a metal to be metallography, but those are for materials that are not transparent, obviously, and we need to use that refracted light because we're looking at a bulk sample that isn't transparent. So those are the two types that we're going to talk about in these cases. So just kind of keep that in mind, especially when we're looking at the illumination system. All right, so now that we're talking about the illumination system, the first thing in a light microscope that we obviously need is light. And so we can look at some of the different sources of how we get that light. So I'll go through a couple that we have. So number one is a low voltage tungsten filament. So these tungsten filaments, these bulbs, what they give us is a continuous wavelength, spectrum of light from 300 to 1500 nanometers. So that's the spectrum of light that we have. So some other characteristics of this: the color temperature is relatively low. So what I mean here by color temperature is that when we talk about color temperature, a lower temperature implies, so let me just expand on that a little bit, lower temp implies warmer, more yellow, red light. So basically, that temperature kind of talks about the types of light that are favored. So in this case, a lower temperature implies warmer, more yellow, red light. So this is something you'll often see if you are shopping for light bulbs in the hardware store, things like that. It may talk about the color temperature in that case, and it's the same idea. The lower temperature, more red, yellow, and then if we're talking about high temperature, which is not the case here, that would be implies colder, what we call colder, and that means more blue light. So it's basically what end of the spectrum are we on that is favored here, right? So continuous spectrum, and we have a relatively low temperature, so more yellow-red color light than blues. All right, so that's the first one. So let's look at number 2. So another source that we have. So this would be tungsten halogen bulbs. All right. So again, these provide a continuous spectrum. But the light is brighter. So when we're talking brighter, again, that's more intensity. And so obviously that's a good thing. And the color temperature, so I'm just abbreviating that temp for temperature. So the color temperature is significantly higher. Than the ordinary ones. Sorry. So our ordinary tungsten bulbs that we just talked about in number 1. All right, so a couple add-ons to note here. So these need some additional stuff. They need what's called a heat filter. And good ventilation. Because we have high filament temperatures. So that high filament temperature presents some issues, but that can be solved with a heat filter and good ventilation. So effectively, to get us that sort of more bright, higher temperature color, we offset that with these additional things that we need. And as you can imagine, anytime you have additional things, the cost of that bulb is going to go up. So that's something to also keep in mind that I haven't explicitly written down here. All right, and third, and lastly, what we'll talk about is a gas discharge tube. So these are tubes that contain pressurized mercury or xenon. So obviously mercury is very toxic, and so that is limited when possible, so it can also be xenon vapor. And they provide extremely high brightness. So the intensity of light is the best of these three with a gas discharge light. So as you might expect, with the added brightness, there's obviously going to be added cost, and added things that we have to worry about. Obviously, one with the fact that if we have mercury, this actually gives us a discontinuous spectrum. So what that means is that instead of having light at all wavelengths, we have portions of that spectrum in which we don't have intensity for specific wavelengths. The xenon, though, does have a continuous, and I'll just abbreviate that as continuous here. So xenon does, mercury doesn't, and also cooling, just like the halogen, is required because of these high temperatures that we have. So again, anytime you have to add additional systems for cooling, for example, there's going to be added cost. And so to get the higher brightnesses that we have with gas discharge or with the halogen bulbs, these give us additional cost. So it's really sometimes a trade-off of what you need and the budget that you have for this system.